All right, so while I'm getting the attendance done, I want you to write that one down and then see if you can figure out which formula of the ones that we showed you yesterday, okay, that we haven't used yet, might apply here. See if you can solve it. All right, I'll give you a few minutes, then we'll go over it. We'll go through the manipulations of that formula just like we did yesterday. So our vector is going to be important on this one. Okay, the ball is initially moving forwards at 25 meters per second, then it hits the sand trap and it accelerates at negative 20 meters per second. That means the acceleration is in the opposite direction, which is why, of course, it says it slows down. Okay, now here's the difference between how this question is worded and how I would word a question. I would say hits a sand trap and slows down, but I would not give you that. That's implied. When I say slows down, it means the acceleration by definition is backwards or negative. Okay? I wouldn't tell you that. That would be one of the things that I would say you've got to be able to recognize that, okay, from reading the story of the question. Okay? So we're trying to find its displacement after 2 seconds. So our givens in this question are the initial velocity, positive 25 meters per second. Okay? The acceleration, negative 20 meters per second squared. And we're looking for displacement, and we're given time. All right, with those givens, which of the formulas from yesterday would I use? Okay, so which formula would fit best there if I've got VI, A, and T, and I'm looking for D? You might need to look at your formula sheet.
I tried to use the one that was velocity initial times time, acceleration times time.
Yep, I would say that one fits well here. Okay, initial velocity times time, I have both of those numbers, plus 1/2 times the acceleration times time squared. I've got the acceleration, times in 2 places, but I have it, so that's fine. Okay, and I have VI as well. Right? That seems like the best one. And I don't even have to manipulate it. It's already set up to solve for D. Okay? It's like the perfect match here. All right, so all I have to do is plug in my numbers in. The displacement is going to be 25 meters per second times 2 seconds plus 1/2 times, and here's where people mess this one up, negative 20. If you forget the negative, you're going to get a ridiculous answer, like this thing went really, really far through the sand trap while somehow slowing down. Okay? You always have to look at your answer and go, does that answer really make sense? Okay? Because sometimes a simple mathematical error, like making a negative positive, will end up giving you a ridiculous answer. Like the question says, this object slows down. Calculate VF, and VF is bigger than VI. Okay? You know you did something wrong in a situation like that, and you just got to figure out what it is. Okay? And then times the time squared. All right, so we've got that. Okay, we just have to plug it in. So I forgot to start my calculator here, guys. So 50 plus 40, 90? Is that right? I shouldn't do math in my head. Is that what it comes up? No, it can't be negative.
Doesn't it have to be?
Sorry, it should be 10, right? Positive 10? I should do math in my head. Okay, 25 times 2, okay, so there's the first part, plus 0.5 times negative 20 times 2 squared. I should do math in my head. The second time, not the first time, where I added them like they were both positive. Okay, so 10 meters, and that would be positive. When something slows down, it's still moving forwards. Okay, so it hits this sand trap and goes forward. Okay, if I forget to make that 20 negative like I did when I did the math in my head, it'll say it traveled 90 meters through a sand trap. You try and roll a golf ball 90 meters on a beach. Okay, like it's just not going to go that far. Sand is a high friction kind of environment. It slows things down very quickly. Okay, so that would be our answer there, positive 10 meters. Okay, everybody all right with that one? This is a tricky formula when it comes to manipulation. So let's have a look at the different manipulations we might be asked to do with this question. All right, let's say the question wanted me to solve for VI. Is there a question?
I was just confused about something. I didn't mean to interrupt.
No, it's okay. If you got a question, I don't mind.
I actually ended up.
Okay, got it figured out?
I got it all figured out.
Okay.
It was just a misconception.
All right, I want to solve for VI. What should I move first? What's not attached to VI right now? The whole other half of the formula, right? Can I subtract that over to the other side? Okay. According to order of operations, I would multiply these two numbers together, then I would multiply these three numbers together, and then I would add them. So it's perfectly fine for me to subtract that whole term over to the other side. Okay, so I'm going to have d minus 1/2 at squared equals vi times t. All right, I still want vi by itself. What do I have to do with the t? Right now I'm multiplying by it, so I would divide. Yeah. Okay, there we go. I'm solving for vi. Okay, d minus 1/2 at squared divided by t. Don't cancel the t's. Okay, in this situation, sometimes people will do that. They're like, oh, I got a t on the top and t on the bottom. They cancel. No, they don't. Okay, they don't cancel in this situation because there's an addition and subtraction operation. This is the top divided by the bottom, right? If this was all multiplication and division, then you could do that. Okay, but in this case, because there's addition subtraction, you can't cancel. All right, so that's going to solve for VI. Okay, so that's one of the manipulations we might be asked to do. Okay, what if I wanted to solve for A? Feels like I should start out the opposite of what I did last time. Instead of subtracting 1/2 at squared, I should subtract the first half, yeah, vi times t. Okay, so I'm going to go d minus vi times t equals 1/2 at squared. Okay, all I've done is just subtract this over to the other side. All right, I'm trying to get a by itself. Those three things are multiplied together. What do I do with the two I want to get rid of? Nancy, what do we do? Divide them over to the other side, right? Okay, that's gone, that's gone. We come over here. Now I'm solving for A. Okay, you got to do a bit of algebra here. Okay, there's no two ways about it. This involves you having to do a lot of manipulating of formulas. Okay. Okay, so the tricky manipulation. Here's the good news. You don't have to manipulate this formula for time unless VI is 0. Okay? Here's why. How many t's are there in this equation? 2. Are they in different places? Yeah. You would have to factor this. We can't guarantee you've done Math 20 when you take this course, so it is not a curriculum requirement for you to solve for t if VI is something other than 0. You will have to solve for t if VI is 0. Why? What's VI times t if VI is 0? Right. So if VI is 0, this formula becomes, and now it's very easy to solve for t because there's only one t in the equation. Okay, so in that case, you would divide the half of a over and square root to get t. Okay, that's the only situation in which you would have to solve for t using this formula. All right? Everybody okay with that? Okay, I want you to try 1 and 2 there. They both use that formula. Okay, so read them carefully, write down your givens. Okay, let's look at the first one here, guys. So skiers moving down a uniform slope at 3 meters per second. Okay, so that feels like that's VI because that's how the thing starts. Okay. Okay, if the acceleration down the hill is 4 meters per second squared, okay, so that would be this. Okay, find the skier's displacement after 5 seconds. All right, this is going to be pretty simple then. I don't even have to manipulate on this one. The formula is already set up for D. So D equals VI, which I have, times time, which I have, plus 1/2 times A, which I have, times T. All right, or T squared, sorry. So when we punch in our numbers here, we're looking at 3 meters per second times 5 seconds, plus 1/2 times 4 meters per second squared times 5 seconds squared. All right, we punch all that in, we should get that this is going to be displaced 65 meters downhill. Okay, if I gave that on a test, how many people would I get not putting downhill on the answer, do you think? Sadly, somewhere between 1/3 and 1/2 of you would forget to put downhill on that answer. Statistically, over many years of teaching this course, okay, I would say that would be the number. Okay, super important to always remember our vectors. Now, number 2, not algebraically difficult. You're just being asked to solve for D. You don't even have to manipulate for that. What are they trying to do in number 2? There's 2 tricks here, right? You have to do conversions. You're given an acceleration in meters per second squared, a time in minutes, and a velocity in in kilometers per hour. Right? You got to make the units match. So remember the magic number for kilometers per hour. It's 3.6. Okay? And you got to convert your minutes to seconds before you can solve this. Okay? Give you another minute or 2 on that one. Okay, so for this one here, okay, first thing we have to do is convert that initial velocity of 100 kilometers per hour to meters per second. Okay, so 100 divided by 3.6 should be like 27. Yeah, 27.7. And repeating meters per second. Okay, and it applies the brakes. Here's the trick I didn't warn you about. That 0.8 needs to be negative. Brakes make you go slower. They produce a negative acceleration. So this is what we in physics call a context-based or a contextual trick. Okay? They are checking to see whether you read the story and can, in a very English 20 sort of way, do a reading comprehension thing that indicates you understood the car was slowing down. Okay? So this has to be negative because it is slowing down. Okay, this is again one of those questions where, okay, when we check our answer, gee, it seemed like it went a long way. Okay, if it was slowing down, should it have really gone that far? Okay, that kind of thing. All right, and our time is going to be 60 seconds. Okay, how far did it travel? So we're looking for D. Okay, so D is going to be VI times T plus 1/2 AT squared. And in this case, that's going to be our 27.7 times 60 seconds plus 1/2 times negative 0.8 times 60 squared. All right, so when we punch all that in, okay, we'll take that number there and we'll multiply it by 60, and then we'll add that to 0.5 times negative 0.8 times 3660 squared. Okay, so it's going to travel to two significant digits, of course, 2.3 times 10 to the 2 meters. Do you need to put a vector on that one? How far is distance? Distance is scalar. Okay? In this case, the displacement would also be that number. It would just be forward, right? But it doesn't ask you that. It says, here's a speed, because it doesn't tell you which direction it's going. All it tells you is it's slowing down. Okay? So in this case, we're only solving for a distance, which does not involve a vector. All right, questions on that formula? We use that one a lot in projectile motion. All right, let's have you write this one down. Okay, I'll give you a minute to get it written down, and then we'll walk through how this one would work. Okay, so in this one here, this is how I would write it. Okay, the speedboat slows down at a rate of 5 meters per second squared. That value is positive or negative? It's negative. It's slowing down. Okay, so the first thing we're told here is that our acceleration is negative 5.0 meters per second squared. Okay, and it comes to a stop. What did they give me there? Final velocity, yep. Okay, process takes 15 seconds. Okay, what's the displacement of the boat? All right, are we using the other formula that kind of looked like the last one? Okay, the first one used VI times T, this one's going to use VF times T. Okay, so we're going to be using this formula here. VF times T minus 1/2 AT squared. All right, since VF was 0, what's VF times T? 0. Okay, so really what I can write here for the next part is 0 minus. Why don't I just cancel it off? I did that in the other one. I just said, oh, well, when it's 0, you just get rid of it. But that's because you were adding it. Now you're subtracting it. So you got to make sure you keep the negative in there, right? So that otherwise you'll get the wrong vector, okay, on your answer. All right, so I'm going to keep the 0 minus here, and then I'm going to go 1/2 times the acceleration, negative 5, times the time, 15 squared. All right, so if I'm going to be using a negative in here, I'm going to multiply all these numbers. That number will be negative, and then I'm going to subtract that negative number, which means my displacement will end up being positive, which it should. The boat's slowing down. It's not going backwards. It's still traveling forwards. It's accelerating backwards, but it is moving forwards. All right, so when we do that, okay, and plug in our numbers here, 0 minus 0.5 times negative 5 times 15 squared. Okay, so it is going to travel 562.5 meters. We only have two significant digits here, so that's going to be 5.6 times 10 to the 2 meters. Okay, that's quite a long way, right? But it must have been going very fast when this all started. It did, after all, take 15 seconds for it to stop. You can travel a long way, okay, in 15 seconds. All right, everybody okay with that formula? All right, let's quickly look at the algebra for that formula. Okay, so D equals VF times T minus 1/2 AT squared. Okay, so if I wanted to solve for VF, what would I do with the 1/2 AT squared? What would I do with it? Add it to the other side. D plus 1/2 AT squared is going to equal VF times T. And then just like the last formula, okay, I would simply divide both sides by T, and I'm solving for VF. This formula works very much like the other one. Okay. Now, if I want to solve for A, okay, I would say in this situation, okay, you can subtract VFT, you can go D minus VFT, but just keep in mind that that's going to be negative 1/2 AT squared when you do that. The negative's got to stay there so I get my vectors right. Okay. If I want to solve for A, then I just go divide by negative 1/2 T squared. Those things come over here. Okay, and I'm solving for A. You just have to watch the signs, that's all, on this formula. Otherwise it works just like the last one. And, just like the last one, unless VF is 0, you won't be asked to solve for T. Okay. Now, if you're being asked to solve for T when VF is 0, okay, this formula essentially comes out to this. D equals negative 1/2 AT squared. So when I'm solving for T, I've got to divide negative 1/2 of A over to the other side. So I'll have D over negative 1/2 of A equals, and then I'd have to square root that. When you're doing this, you'll know if you forgot to bring the negative with you. Because what will it tell you? Error. Yeah, your calculator will have a conniption fit because it'll tell you it's impossible to take the square root of a negative number. Okay, so if that ever happens, you forgot to bring a negative over somewhere. Okay, or maybe the acceleration was negative and you forgot to make it so, something along those lines. But the calculator will tell you. Okay. All right. Let's have you guys try that one. Both of those, actually. All right, so on number 1, okay, we're talking about aircraft landing on an aircraft carrier. So there's these like cables that go across the deck, and they've got a little hook that drops out the back of the plane, okay? And then when they land on the deck, the hook catches the cable, and the cable literally like jerks them to a stop. Because there's no way you could stop a plane on the short runway of an aircraft carrier just using its brakes, okay? Like it would just go off the end every single time. So they have these arresting cables that help yank it to a stop, basically. Because this is, you need a chiropractor kind of acceleration, okay? If you've ever seen, like even, in like Top Gun and things like that, where they, they show them coming, their heads like snap forward, okay? Because it's a violent stopping action that gets them to stop that quickly. Okay, so the aircraft stops. What are they telling me there?
VF is 0.
VF is 0. Okay, it's again one of those contextual clues. Okay, VF is 0 meters per second. We know that D is 150 meters. That's going to be forward because you move forward while you're stopping. Okay, and the acceleration is going to be negative 15 meters per second squared. We're looking for T. Wait a minute, didn't Coder tell me you'd never have to use this formula to solve for T? Unless VF is 0, which it is. Okay, so D equals VF times T minus 1/2 AT squared. VF is 0, so I'm just going to take all of that out and leave the negative there. All right, so D is going to be negative 1/2 times negative 15 times T. So, oh, no, sorry, I'm looking for T. Then I got to solve for T. Sorry, guys. All right, so I want to solve for T, so I'm going to divide negative 1/2 and A over to the other side. So what I'll have is this, D divided by negative 1/2 of A equals T squared. I don't want T squared, I want T. So I have to square root both sides. So that's going to be 150 meters divided by negative 1/2 times negative 15. Okay, that'll equal T. All right, so 150 divided by negative 0.5 times negative 15. Okay, then I got to square root that. All right, it's going to take 4.5 seconds. We got 2 significant digits there. Okay, everybody all right with that? Okay, how many people have done the second one? All right, we'll give you a couple more minutes on the second one. All right. let's look at the second one here. What do you have to do in the second one before you can do the acceleration part? You got to convert the kilometers per hour to meters per second. Okay, so that'll be our first thing. 160 kilometers per hour, okay, divided by 3.6. Okay, you're looking at 44 meters per second. All right, so that's going to be our VF, 44.4 meters per second. Incidentally, that's 100 miles an hour. Okay, so this Corvette is accelerating from 0 to 100 miles an hour. Okay, that's stinking fast. Okay, lots of passenger vehicles can't go from 0 to 100 kilometers an hour that quickly. Okay, so this is a super fast car. Okay, it also consumed fuel at a ridiculous rate. Okay, it was very, very thirsty. Okay. Now we know the time, 6.2 seconds, okay, and we know that it traveled 220 meters during that time. We're looking for the acceleration. All right, so we've got D equals VF times T minus 1/2 AT squared. All right, so if I'm trying to solve for A, probably the first thing I'd want to do is subtract VFT over to the other side. So I'd have D minus VF times T equals negative 1/2 AT squared, and then I would bring the negative 1/2 and T squared over to this side, so I'm solving for A. All right, so if I'm plugging in my numbers here, 220 meters minus 44.4 times 6.2, and then divide that by negative 1/2 times T squared, which was 6.2 squared. Okay, so 220 times 6.2, or sorry, no, 220 minus, sorry, I gotta see my writing here, I guess 44.4, that number there, okay, times 6.2. Okay, and then I'm going to divide that by the bottom, which is going to be negative 0.5 times 6.2 squared. Whoop. Don't need two negatives there. I'm not going to like that. Okay, so it looks to me like the acceleration to two significant digits is going to be 2.9 meters per second squared. Okay. That means you would feel sufficiently pushed into the seat, okay, by the acceleration of that car. Okay. About 1/3 of the weight you feel normally would be how much you'd feel pushing on you from the car's acceleration. All right, questions on that? Okay, we've still got one more formula to go over. Okay, the one with all the squareds in it. All right, so copy that one down and we'll talk about it here in a minute. So let's have a look at this one here. So the way a gun basically works, guys, is obviously the hammer hits the back of the bullet, okay, in the back, the round of the bullet, okay, there's a little ignition thing in there that ignites the gunpowder. The gunpowder explodes, forcing the bullet out of the barrel of the gun, okay. There's an incredible amount of acceleration produced by the expanding gases from the explosion of gunpowder, okay. That is all contained within the barrel of the gun, all right. So that expanding gas has nowhere to go except to push the bullet out the barrel, and then it can escape out the barrel after the bullet. So there's a lot of force involved there, which is why it can produce such an incredible acceleration, okay? Over 53,000 meters per second squared, all right? Like, if a bullet wasn't made of metal, it would be liquefied, okay, by that kind of acceleration, all right? So it's a huge amount of acceleration. So that's one of our givens, okay? That A is 5.35 times 10 to the 5 meters per second squared. Okay, and we know the displacement, or the distance over which that acceleration is going to occur, the length of the gun barrel, .750 meters. Okay? With what speed does the bullet exit the barrel? So we're looking for VF. What can I assume is true here?
VI equals 0.
That VI would be 0. It doesn't say that the person who shot the rifle was running when they shot it. Okay, so in this case, we would have to assume that they were stationary. That's generally how you are most accurate, okay, in your shot. So we would assume here that VI would be 0 meters per second. Whoop, just meters per second. Okay, I only have one formula that contains VF, VI, A, and D, and it's the only one we haven't done yet. VF squared equals VI squared plus 2AD. Okay, this is the one that doesn't involve time. So I'm looking to calculate VF, the speed the bullet exits the barrel at. Okay, in other words, what we call muzzle velocity. Okay, so I'm just solving for VF, but this formula calculates VF squared. So what do I need to do to the other side? Square root it, right? So I'm going to have VF equals the square root of VI squared plus 2AD. Then I can just plug in my numbers. So the square root of 0 squared, which is 0, okay, plus 2 times 5.35 times 10 to the 5 times 0.750. Okay, so when we punch all that in, okay, so I go square root of, okay, 0 squared. I wouldn't really have to enter that, but I will, okay, plus 2 times 5.35 E5, okay, times 0.75. Okay, so the bullet leaves the muzzle or the barrel of the gun at 896 meters per second. Is that fast? Okay, it's pretty close to 3 times the speed of sound. Sound travels at around between 300 and 330 meters per second, okay, depending on temperature. Right? So the bullet's going faster than sound. What does that mean if you're the target? Well, in the Army they have a saying. You never hear the bullet that kills you. Because it's traveling faster than the sound of the explosion that propelled it. Okay? Scary thought. Okay? That means that expert snipers take out their targets, and those targets never know. Okay? They'll never hear the sound of the shot. Because the bullet will get there before the sound of the shot. Okay. Longest sniper shot ever was, up until November of 2023, held by a Canadian sniper. In November of 2023, the record was broken by a Ukrainian sniper. 3.8 kilometers. Okay. They hit their target, which was a person, okay, from 3.8 kilometers away. Okay. That bullet would be in the air for a very long time. To make a shot like that requires not only incredible nerve, but also incredible, like, calculations and things like that. You would have to have, and most of them do, have a spotter. Okay? The spotter tells them things like wind, drop, okay, things like that. Because you have to remember, and we're going to talk about this in projectile motion, which is why I talk about it a little bit now. Okay, as soon as that bullet leaves the barrel of the gun, it's not just traveling forwards, it's also falling. Gravity is pulling on it. Okay? In the first second it's in the air, it'll drop 4.5 meters. Okay? So the longer it's in the air, the more gravity pulls it down. If you're shooting at a target 3.8 kilometers away, you're aiming several meters, and by several I mean like 30, okay, over it. Okay, you don't put the person in the crosshairs, you aim way above it. Well, actually, what you do is you adjust the scope, so the scope is pointed at the person, but the barrel is pointed way above the target, okay? And that corrects for the drop of the bullet over the course. It's hard to picture with a bullet because they go so fast, but if you've ever used a bow and arrow, you can tell. Like if you aim for the bullseye and you let this go, it's gonna hit below the bullseye. Gravity will just pull it down as it travels, okay? So there's a lot of things, not just gravity to consider, but any crosswind as well. Over 3.8 kilometers, there could be a lot of movement of the bullet from side to side and up and down. Okay? So to hit that kind of, that's somebody you want as your friend, not your enemy. Okay? Because that's a long way. There are people out there who are that skilled. You can either take comfort or be terrified by that thought. I don't know, that's totally up to you. Okay? But there are people out there who are that talented. All right, so almost 900 meters per second. Bullets travel really fast. Obviously, it's dependent on the type of weapon that fires it. A pistol does not have that kind of muzzle velocity, okay? But a long rifle like a sniper would use absolutely would. Okay, let's have you guys try just number 2 for now, because number 1 you can actually use like 2 different formulas for. So don't worry about number 1. Let's just do number 2, okay? So on-ramps are designed so that you can seamlessly merge into highway traffic. That's what they're designed for. They're designed very well, provided you understand that it requires you to press the pedal on the right. Unlike some people who don't understand that and try to merge into 110 kilometer an hour traffic at 65. If you're that person, I'm the person whose grill is right behind your back window, okay? Because that annoys the hell out of me, okay? You gotta merge. I don't wanna die, okay? And that means we have to go faster. Sorry, pet peeve. Was that rant over? Okay, go fast, please. When you merge, go fast, okay? All right, so we want to go, okay? The car needs to merge, it has to increase from 50 kilometers an hour to 100 kilometers per hour in that time. So first we have to convert those to meters per second. Okay, so very quickly, okay, we'll go 50 divided by 3.6, okay, so that's 13.8 repeating. Okay, and then VF will be the 27.7 repeating, okay, meters per second for that one. And we'll actually get that number so that we have it for the calculation. Okay, so those are our 2 speeds, right? And the engine can provide a maximum acceleration of 3.8 meters per second squared, because it's not just the engine, you also have the downhill part. Okay, most of the time an on-ramp is, giving you a gravity assist by being tilted. Okay, so our acceleration is 3.58 meters per second squared. All right, we need to find the minimum length of the off-ramp. This is exactly the kind of calculation that a road designer or urban planner or whatever is going to undertake in order to figure out how to design an interchange so that it is safe. Okay, and a good interchange, not like the ones in Calgary that all have stoplights on them. Okay, have you ever noticed that? Okay, a good interchange should never have stoplights on it, because that's not efficient. The more you have to stop, the more fuel you consume, and the harder you have to accelerate to get up to highway speed. Okay, so a true interchange has no lights on it. Okay, so that way you can continue to move efficiently. So we are looking for D. All right, so obviously this is the formula we're going to have to use. All right, and we got to manipulate for D. So what's the first thing I should move? What's not attached to D? VI. Okay, so I'm adding VI, so I should subtract it. So I'm going to have VF squared minus VI squared equals 2AD. All right, I'm looking for D, so now I just divide both sides by 2A. And I've got D. If I wanted to solve for A, I'd divide by 2D. Okay? It's not a difficult formula to manipulate. So now that we've got that set up, now we can just plug in our numbers. So D will equal, right, 27.7 squared minus 13.8 squared divided by 2 times 3.58. Okay, so there's the top, going to divide that by the bottom, 2 times 3.58. All right, so it's got to be, I've got 80 meters here. Did I mess something up? Is it 3.85? Oh, it's 3.8. I put 3.58, that's why. Sorry guys, I messed up I kept writing 3.58, it was supposed to just be 3.8. So if I put 3.8 in there, I would have got 76, but we'll just put it in for argument's sake here. Okay, they're 76 meters long. So that on-ramp would have to be 76 meters in length in order to get us up to 100 kilometers per hour. Okay, that's providing we're not driving Miss Daisy, okay, and we're using the pedal on the right to get going, okay, and get up to speed. Questions on that one? Okay. All right, I would like you guys to try, let's say, number 2. Number 4. Number 5. Let's say we'll do those 3 and then we'll call it a day.